Here's a nice comprehensive thermodynamic problem that actually ties in equilibrium as well. In this problem, they're asking us to find delta H, delta S, and delta G standard, all using the summation equations. They even make a note here. It says calculate all thermodynamic values from Appendix 4. In other words, if you get two of those quantities, you could always find the third using the Gibbs equation, but they're saying no, use Appendix 4 for all of these in the summation equation. So we'll do that. We'll obey. It's not as much work as it seems. We only need to look up hydrochloric acid, at least for the heat of formation. It's negative 92. And for the diatomic molecules, well, without even having to look them up, you know that they're 0. So that's negative 184 kilojoules. Entropy values, however, are not 0 for elements or diatomic molecules, so we do have to look up those. In the case of hydrogen, it's 137, and for the chlorine, 223. Now these are in units of joules, not kilojoules. So we get 20 joules per degree Kelvin. And now the last summation equation, the free energy of formation. Yes, we can look up this in Appendix 4 as well. It follows the exact same format as the other summation equations. It's just a different quantity we're looking up. And like heat of formation, the free energy of formation will be 0 for elements and diatomic molecules, so you don't have to bother looking up hydrogen molecule or chlorine molecules. And that works out to be negative 190 kilojoules. Okay, so now we've got values for delta H, delta S, and delta G, all standard. And they want us to find K. Okay, that's interesting. If they want us to find K, that is the equilibrium constant K. We're not talking rate constant K. This is equilibrium constant K. Think all the way back to chapter 13. Well, there's one equation that involves K. Delta G standard equals negative RT ln K. And the R, of course, is the universal gas constant. Now, there is a little bit of a problem. We probably are more familiar with the universal gas constant in units of joules per mole times degree Kelvin. So we got 8.3145. But if delta G standard is in kilojoules, we need to convert one of those into the other. It actually doesn't matter which one. For kicks, let's divide the value of R by 1,000 and get 0.0083145 kilojoules per mole times degree Kelvin. And then we can just plug in. So negative 190, we got that from above, equals negative 0.008345. They gave us the temperature. If you look at the question, it says way at the top, find K at 298 Kelvin. Okay, so if they give us that, then we're going to follow what they gave us. And we've got a natural log. Okay, so let's simplify a little bit. after doing a little dividing, we find that 76.7 equals the natural log of k. How do you undo a natural log? Take e raised to both sides. That gets rid of the natural log. So k, the equilibrium constant, equals the number e raised to the 76.7 power. Punch this into your calculator and you'll see something enormous. 2.01 times 10 to the positive 33rd. So that's a huge, huge value of k. This is a very product-favored reaction. Let's take a look at the rest of it here. And this is a nice connection to what we already know about equilibrium. If all of the gases are placed in a flask such that the pressure of each is 1 atmosphere, which would be standard pressure, in which direction will the system shift to reach equilibrium? Well, I can tell you just eyeballing it, if you have a huge, huge, huge K on the order of the positive 33rd power, I can almost guarantee without picking up a single pencil here that it would be a shift right because of the huge value of K. But let's verify that. We have a nice equation. Let's write the reaction quotient Q. Don't forget to raise to the power of the coefficients. And if they're saying that the pressure for all of these is 1 atmosphere, that would be 1 squared over 1 times 1, that's 1. Is 1 less than or greater than 2.01 times 10 to the positive 33rd power? Let's say much, much, much less. And so when Q is less than K, we shift to the right. So yeah, our hunch was verified.